What is the RLD? Why is it useful? How it works? And finally, how it can be helpful to this project. Let's answer these questions one by one. Before we start, if you're new here, this series is all about trying to recreate Meta's EMG wristband from scratch. We are going to explore the hardware, electronics, machine learning and everything in between. So if you want to follow the entire journey, make sure to check out the playlist. The right leg drive, or RLD, is a circuit used in biological signal acquisition systems such as ECG, EEG, and of course EMG. Despite its name, it is not necessarily related to the right leg. The name comes from its original use in ECG systems, where the feedback electrode was often placed on the patient's right leg. The purpose of the RLD circuit is to reduce common mode interference, especially the 50 or 60 Hz noise generated by electrical power lines. This noise is a big problem in biopotential measurements because biological signals are extremely small, often in the range of microvolts or millivolts, while the human body can pick up much larger interference signals from the environment. The main idea behind the RLD is simple. Instead of just rejecting the interference after it enters the system, the circuit actively measures the common mode noise and feeds back an inverted version of it to the body, reducing the interference before it reaches the amplifier. In other words, the RLD is an active negative feedback system used to balance the patient's common mode voltage. To fully understand the RLD, we need to firstly understand the problem it solves. The main issue is electromagnetic interference, or EMI. As explained in this Texas Instruments application report, in a ECG system a large amount of EMI can be coupled to the patient's body through the skin. The interference can also enter the system through parasitic capacitances between power cables and the human body, power supplies and the electronics, cables and the surrounding environment. Even though this example refers to an ECG system, the same principle applies to EMG acquisition systems. At this point, you may ask, if we are using a differential amplifier, shouldn't this noise disappear? After all, the interference reaches both electrodes, so the amplifier should reject it as common mode noise. And in theory, yes. A perfect differential amplifier would completely remove a signal that is identical on both inputs. However, real systems are not perfect. The problem is that the two paths are never exactly the same. The electrodes do not have the same impedance, the cables are not identical, and the protection circuits and filtering components also introduce small mismatches. Because of these differences, the interference is slightly modified on each input path. For example, instead of having the same voltages of noise on both electrodes, we may have 0.99 voltage noise on one electrode and 0.98 voltage on the other electrode. The amplifier now sees a difference of 10 mV. The common mode interference has been converted into a differential signal. And once the noise becomes differential, the amplifier cannot distinguish it from real biological signal. Now that we understand the problem, we can introduce the RLD. There are different techniques to improve common mode rejection, and the TI application report discusses several of them. However, the RLD is one of the most interesting solutions because it does not simply reject the noise, it actively reduces it. The idea behind the RLD is a negative feedback loop. The circuit first measures the common mode voltage present at the amplifier inputs. This means it calculates the average voltage between the two electrodes. Then an amplifier generates an inverted version of this signal and feeds it back into the patient's body through the RLD electrode. So if the body is being driven by a 50 Hz interference signal, the RLD generates an opposite signal that cancels it. It works exactly like a control system. Measure the error, generate a correction, and reduce the error. At the end of the application report, Texas Instruments tested the RLD technique using the ADS-1298, which is a low-noise analog front-end designed for biopotential acquisition. Without the RLD feedback loop, the system achieved a Coleman mode rejection of around 81 dB. After enabling the RLD feedback, the rejection improved to more than 93 dB. This means that the feedback loop was able to significantly reduce the amount of 50 Hz interference reaching the measurement system. I decided to make this video because the right leg drive is a topic closely related to the ADS-1298, which I mentioned before. I'm currently interested in building a proof of concept using this chip, and before jumping into the hardware, I wanted to understand and explain one of its interesting features. Thanks again for watching, and I'll see you in the next one.